Right. It's like
It's branches. There's nothing fundamental about the branches. It's just the way the wave functions. It's the way the whole wave functions. So you don't have to have a special wave function branch. Well, there will be. No, it functions fundamentally. But you don't have to add worlds.
And then we say, okay.
Expositions doesn't make it sound like you do it.
Let me just try this. So, okay, if you can just do it, you can do it with these forward, backward, if that's okay.
Okay. Wallace's book.
The Zoom, it's okay because
See it. They're very good.
no, don't do that. No. Okay.
Tim's criticism.
I want the Zoom, there's a camera up here. Right, there's a camera up here, so I want that to be.
Oh, I see.
Do is
And then, and I want to record off this screen.
and they're
It's not showing up.
Doesn't really give you.
How's your shuffleboard?
Charitable way.
Not as bad as it always is.
It's the only thing I.
You could imagine.
I wanted to record you from this camera. Start video.
I feel like,
and all the way.
you were clearly
I'm on the cusp.
He's recording maybe.
Can I apply for a few more games?
This is what I want. That's the more money on them to get it to do that.
It's a neat place though, right?
The cat's
December is
We had, of course, anyway, people are gonna wanna see this, see that, this, that's fine.
95.
I did you want to explore now, which evolves probabilistically, which gets your cats raised. No, seriously, I said that thing you could add is mine. Absolutely fair. Many minds.
Certainly, if people could see this.
Never seen that paper on this got published. My fault. I
Okay.
didn't have a footnote instead.
Maybe it means if they smell it.
You would introduce John? I know that some
Okay.
other people said they're coming.
Okay, quite a few
What?
visitors.
Some other people
So
said
other people said their comments?
who weren't here yet.
Oh, okay. Well, then we can wait another couple minutes.
David.
Yeah, David is supposed to show up, that's true. All right, so just relax a little bit.
But just to make sure when it's come to be seen.
Okay, so you're. You?
There's a camera on this
Back in the day.
screen, okay? So as long as you're standing in front of me.
What is there like another salad?
It's an interaction
Of this, you're visible from there.
rather than the ways.
One of Holiday Forest
And it's a very straight eye point.
I'm afraid so. I
That's
don't
okay,
know.
that's okay.
Somebody might have a point.
There's a branch.
I actually wrote a paper.
One of which is.
Not really about answers. But this is basically about simulations.
Yes. Well, no, it's in. It's just, no, results in it.
So it's the system we call measurement.
Yeah, so measurement,
Is that what produces the brand?
as Jean, I think we'll talk about, sensible, he doesn't have many worlds of interpretation. He does have the wave function, and it is going to evolve.
What is some great, my favorite question.
But it is a Bohm interpretation, it goes more than so. So that's the big, when there's a measurement, there is an interaction. There's those particles move around. It's fun to talk about this later. So maybe we can begin in this way. Maybe I just want to mention that this is the last MAPS talk. So some of you are here that aren't regular people who go to the MAPS stands for Metro Area Philosophers of Science. We've had lots of great meetings. This semester they've been taking place sometimes here, but mostly at NYU near Lincoln Center because it's a nice room. What did I say?
NYU.
You know what I'm thinking about? The reason I like it is that it's right next to Lincoln Center. And I like going to things at Lincoln Center, so I fit the two together. Unfortunately, I got tickets for something at Lincoln Center today. That's going to cause me to run away. But I just want people who don't come to these regularly to know about maps. It's been a very good thing, and Vishnu is going to take it over next year, and we'll run it much more efficiently than I've run it. And it has a website that you can look up, and you can see all the interesting talks over the years. And I would like it to be a little bit involved, like Paul. I'd like you to come to these things too.
Me too, I would like.
But you could have known about them because you're on the mailing list. Okay, and this is the last one of this year, and it's really fortunate that we have Jean-Brice Mont here, that whose Tim is now going to introduce, and he's going to give us a talk. And the people who aren't here, come and light screw them.
I just saw. Where is Jean? How can I introduce Jean?
Vanished.
I'll be back in a second. Don't give my slide.
Jean is a biochemist who works on invisibility.
Well, particles sometimes go out of existence.
Hey, buddy.
It's going to bury because
I don't know if you're a regular, if
Okay,
to the maps.
Let's go, we'll stop, John.
Okay, so.
He's not here?
No, well, we're just gonna start. We decided we've waited long enough. So, this is Jean-Brice Mont, for the few of you who maybe don't know Jean, who has been working on many things, but especially foundations of quantum mechanics in a very rhetorically spicy way for some years.
Let's see.
So this should be a very enjoyable talk.
We'll see. Okay, thank you very much for the invitation. It's a bit difficult talk for me because it's a diverse audience, and so I don't know if people, I mean, I was told by some people that my talk will make people very upset. And Barry said, no, you're going to preach to the choir. Everybody, I am desperate to find some opposition, so I'm not sure what to believe. Anyway, I will make rather, I hope not too long talk, but I will try to cover every possible, at least not every because it's too much, but every possible interpretation or the type of interpretations of quantum mechanics that I know, and criticize them, and then try to explain why I think the only reasonable one is the Broglie-Bohm theory, or the Bohmian mechanics situation. So I start with a quote from David Mermin, who's a physicist at Cornell. It's a new interpretation appears every year, none ever disappear. This is of course not very good. And my goal is to try to classify those interpretations and see what's wrong with most of them. Okay. So in particular, since Barry thought I would be too uncontroversial, I want to challenge an idea which is rather widespread, that we have only three possibilities. Either the wave function is not everything, so we have to introduce so-called hidden variables, or the Schrödinger equation is not always correct, so we have to introduce GRW, Weber, or collapse theories, or experiments do not have unique outcomes, and then we have to do many worlds. This is usually a trilemma, but I don't agree that there are really three possibilities or three realist alternatives. But before doing that, I will phrase the problem of quantum mechanics in a slightly unconventional way, not for some people in the room, but for most of the literature, and consider some other solution, which I think don't work, but still. So I want to, there is a famous article by Bell called Against Measurement, and I want to do something which will be against the problem of measurement. Because the usual way to formulate the problem of quantum mechanics is to say that Schrödinger cat can be in a superposition of psi cat alive, plus psi cat dead, and that Schrödinger said can't be a possible complete description of the cat. It is obviously either alive or dead. By the way, he never thought there would be both, okay? In his article, he calls it, in English, it's called quite ridiculous, the example. It's meant to be a reduction ad absurdum of the idea of macroscopic superposition. And in German, it's called burlesque. Anyway, the way out of this problem from the point of view of ordinary quantum mechanics is the collapse postulate. When you look at the cat, you see if she's alive or dead, and then you reduce, you take one of the pieces of the wave function, and you take also the piece of the particle that was measured, and is coupled to the state of the cat. Of course, it's more realistic to say that the wave function of a pointer going up and a pointer going down or something like that if you do a spin experiment and you have two possibilities. But Schrödinger had this idea to couple the experiment to a cat, and that made it more lively, if you can say it like that. Since this is maybe not, I don't know what's the word, but more spicy. This is a Deus ex machina from the point of view of the linear Schrödinger evolution. It's never going to get you the cat alive or the cat dead. So justifying this Deus ex machina is viewed as the main problem. But I claim, and maybe it's better if David Albert is not here, that there is a deeper problem, which was pointed out to me by Shelley Goldstein, that, you know, I don't say invented it. Neither psi-cat alive nor psi-cat dead are cats. These are functions defined on the space of position of all the possible particles of a cat. It's a function on a high-dimensional space, forgetting about the spin, which makes things more complicated. And cats are located in R3, like you, like me, like the family. And it's not clear what it means to say that psi-cat are descriptions of cat, let alone complete descriptions of them. Of course, you can use them to predict results of measurement on the object that they describe, but nothing else, and that's exactly the deeper problem of quantum mechanics. What many people do, and I think I've done that before, is mentally identify cats and wave function of cats. But that's exactly what I think is illegitimate. De Broglie said already in 1927 Solvay conference, it seems a little paradoxical to construct a configuration space with the coordinates of points that do not exist. And like the Magritte painting, which you maybe know, this is not a pipe. A wave function defining a set of points that would constitute a cat if those points corresponded to particle position is simply not a cat with nanoparticles. Anyway, but the problem, and that I maintain as the deeper problem, occurs even for one particle. Because if you take an electron out there and give you its wave function in every detail, and I ask you, what does it mean? The only honest answer a physicist can give is to say, if I take this electron in a laboratory and make such and such experiment, I'll get such and such result with such and such probability. But it says nothing about the poor electron out there if you don't bring it to the laboratory. I want you to contrast that with classical mechanics or celestial mechanics. If I say the moon or any satellite will be at some place in the sky in 6 months, I mean it will be in some place in the sky in 6 months. I don't mean, the meaning of the statement is not that if I look with a telescope, I will find the moon there. That may be true, but that may depend whether the sky is clear, whether the telescope works at advertised, and everything that philosophers call additional assumption. Celestial mechanics per se says nothing about the telescope, but it tells you where the moon will be. Of course, you have to believe that the moon is there when nobody looks, but that I believe. And of course, then to take the famous question of Einstein. So you see, the meaning of statement in physics do not refer to observation, the meaning. Of course, physics is checked by observation, it's checked by experiment, but it's not about experiment. Quantum mechanics is a science which, if you take it strictly speaking, is about experiment. And that is the deepest problem. It's the problem what things mean in nature, okay, out there, outside of laboratories. And that's the meaning. And since we are in the philosophy department, I'll be not afraid to call it the ontology problem, because in physics, they wouldn't know what I'm talking about. But, okay, so I will go to a series. I'm sorry, some people may know it, not like it. I'll get to things that maybe people like, so it will be less non-controversial. But I will start with things which maybe everybody knows and doesn't like. The first class of solution, quotation mark, is simply those that ignore or will understand the problem. You try to find some recipe that will make the macroscopic superposition disappear in laboratory experiments. You are still talking about laboratories. And this, of course, includes Copenhagen, which is sort of vague, but also interpretation that make a principal distinction between the quantum system and the measuring device of the system's environment. Well, these are two people in France, which you probably don't know. Rovelli, you probably know, it's also in France, but you probably know. The relational interpretation, to the extent that I understand it, seem to be in that category. And any interpretation, many of them that rely on decoherence alone and ignores the meaning question. So they say, well, two-wave function of macroscopic bodies do not interfere with each other. So, I mean, they don't overlap. And then you can choose whichever one you want. You can take the wave function. But that, of course, depends on what you look at. The wave function by itself doesn't say anything, you know. And of course, there's the problem of meaning. So committed to the flames. That I know at least. Now, I want to go, people will probably think I waste your time, but anyway, I think it's maybe pedagogical, especially if it's recorded, that what is called cubism, which has become a fad recently, and which I'd call a further step in the wrong direction. Yeah?
There it is.
Yeah, okay, good. He comes after, after the part which we will agree with. So anyway, so people like Fuchs, Mermin, Perez, and Schack, I mean, they're the four one. I put forward the idea that, and that's sort of quantum Bayesianism. That's what cubism means. All the quantum states represent individual subjective probabilities about certain events. And they write, the time dependence of the wave function does not represent the evolution of a physical system. Good. It only gives the evolution of our probabilities for the outcomes of potential experiments on that system. So of course, they limit only science to potential experiments, and that's the only meaning of the wave function. Therefore, there is nothing surprising in the collapse of the wave function, because it's like if you throw a coin, then it will be heads or tail, you don't know. If you look, you know, then you change your probabilities, right? I mean, if you learn something, that's Bayesian updating. If you know something, you change your probabilities. So I update my quantum state when I learn something after a measurement, and Fuchs, Mermin, and Schack explain quantum state determine probability through the Bohm rule. Since probabilities are the personal judgment of an agent, it follows that the quantum state assignment is also personal judgment of the agent assigning that state. The notorious collapse of the wave function is nothing but the updating of an agent state assignment on the basis of her experience. But what is the information about? It is sometimes suggested that the information is only about the macroscopic world, or even only about the result of measurements. And Fuchs and Perez write, the threat, that's very funny, I think, but anyway, I will read it. The threat common to all the non-standard interpretation, which of course include GRW, Broglie-Bohm, etc., is the desire to create a new theory with features that correspond to some reality independent of a potential experiment. Oh my God. People want to speak of a reality independent of an experiment. How do they dare? Contrary to those desires, quantum theory does not describe physical reality. Ah, good. I'm reassured. What it does is provide an algorithm for computing probabilities for the macroscopic event detector clicks that are the consequences of our experimental intervention. The strict definition of the scope of quantum theory is the only interpretation ever needed, whether by, of course, I have a slight moral problem there. So I shouldn't do ethical philosophy because that's a touchy subject, but still, why on earth do you do experiment in the first place? If you're not checking your theory about the world, you go to the government and you say, I want $1 million, etc., to do a costly experiment. And they say, what do you want it for? We want to study the laws of nature. And then you go to these guys in the seminar, they say, no, there is no nature, we don't talk about nature, we just do the experiment for the fun of it. I mean, or maybe not for the fun of it, but I don't know why. And then, of course, if now there is a spy from the NSA is listening to you and then reports to the government what we are saying in our seminar, I'm not going to give you any money, I can assure you of that. Anyway, this is not taken seriously. Travis Norson has called cubism solipsism FAPP. The acronym FAPP means for all practical purpose, which is something that Bell used in his writing for St. Quantum Mechanics works, FAPP. Of course, they claim not to be solipsis, but if physics is all about updating my subjective experience, then in what sense does it differ from solipsism? Maybe one call it solipsism in denial because they don't say anything about except their subjective experience, okay? But they don't say what could exist outside one's own conscious state of mind.
Barry had questions.
Just a remark. I understand why Fuchs and Perez hold this view, because if they don't interact with people who hold sensible views, they're not real.
Ah, that's good. That's a way to see it, yeah.
A quick
But they do interact, they did interact with me at least. I don't know if you hold sensible views, but I already.
A quick technical question. So the quotation, I think, comes from an article in Physics Today that's either 2001, 2002.
I remember, I have it in my book, but I don't.
And I'm just curious because I don't understand, I don't know enough of the history of Cubism to know whether they wrote that before the onset of Cubism or after, whether that was representing Fuchs's views before he got in the business of quantum interpretations or after. I've always wondered that question.
I have my book in my computer, but I would have to look there. All these quotes are in my book, but you know. Anyway, you see, when you do standard probabilities, for example, you can say that a coin has two faces and a dice has six faces, and these are properties about which you have probability. You say they are equal probability, or maybe they don't have, never mind. But there are certain properties of the world about which you assign the probabilities, but here it's unclear what are the properties to which cubists assign their subjective probabilities, except their personal experience. Now, I found a quote, which I knew already, by Einstein, 1949, in this book about Einstein, philosopher, scientist, and about Copenhagen, or at least the idea that you can only talk about measurements and not reality. He said, what is dislike in this kind of argumentations, basic positivistic attitude, which from my point of view is untenable, and which seem to be to come to the same things as Berkeley's principle essay is perceiving, which of course, you know. So I say the cubists are the real heirs of Copenhagen, committed to the flames. So now I want to go to something which probably you don't know and which is not, except rarely defended explicitly by people, but is, I think, in the back, I'm absolutely convinced that's in the back of the mind of most physicists who don't care about quantum mechanics, and that's what's called a naive statistical interpretation. And maybe it was also the view of Einstein, because a state psi, like a probability distribution or a measure in statistical mechanics, does not represent an individual system, but an ensemble of systems. And any observable represented by an operator A, there is for every individual particle a value V of A that the measurement of A would reveal and not create, and it pre-exists to every measurement. That's what people call a hidden variable. The physicists hold that view don't want to speak of hidden variable, but that's a confusion of terminology. The fact is that that's what they have in their mind. And so there's nothing surprising again with the collapse, because it's like looking at a coin and I see which side it is on, and then I update my probabilities. They don't need, they may have, this is a perfectly objectivist view, there is nothing funny philosophically, etc. And in fact, if it worked, it would be wonderful, okay? So to continue with what it means, if you have a state psi that you decompose into a basis of eigenvectors of A, with eigenvalues lambda n, the frequency, just empirical frequency when you repeat the same experiment, the same psi, with which one obtain the result lambda n, will be the absolute value of Cn squared, which is the Bohm rule, okay? And that's a very, I think it's a very, it doesn't work, but it's a very sensible view. And however, there's a well-known property of quantum mechanics. If two operators commute, then they are simultaneously measurable. You can do it simultaneously, and also their product. And then the value that I discussed of the product is the product of the values, and the value of the sum is the sum of the values. These are properties. Predictions of quantum mechanics, which people who have the view that I mentioned must be committed to. However, that view is flatly contradicted by what are called the no hidden variable theorem. And these are, I will say the theorem, but they are very, very unknown in physics. And I think it will be very useful to be taught in every physics class. So let A be the self-adjoint operator in a Hilbert space, mean a vector space, okay, of dimension at least 4, okay, nothing very fancy. Then it's just a fact that there is no map so that V of A for every operator is an eigenvalue of A, and whenever they commute, either the product rule or the sum rule holds. Just a fact. If you assume this, either that and that or that and that, then being clever enough and playing with Broglie matrices and so on, you can derive that 1 = -1 or something like that. So there just doesn't exist a map. Okay. So these theorems are due to Bell-Koch and Specker, with simplified proof due to Mermin and Perez. So you cannot have a statistical distribution of maps that do not exist. The naive statistical interpretation says that you have a statistical distribution of these maps, but they don't exist, so you can't have. I say it may be obvious to you, I don't know who are you in the room, so, but these terms are very much ignored in the physics community. And I believe all the talk around the idea that quantum mechanics is only about information is implicitly a naive statistical interpretation, because information should be information about something else than itself, okay? If I tell you, I don't know, about some historical event, then I inform you about something that happened in the past, and it's not information. That is not information. And of course, this interpretation would make sense, this talk would make sense if the naive statistical interpretation was standalone. And I will even add that maybe that interpretation, what cubists mean, or this, that would be a charitable interpretation of their view, but it's definitely not what they say. I must add, and that's, I hope to discuss it with Tim later, is that there is another argument against this, as well as against cubism, based on the so-called PBR theorem that is given in Tim Mauldin's book, but I would like to see the relation between the two, but that's something we can discuss. Anyway, committed to the flames.
You're going to create a gigantic fire, gigantic forest fire. It's going to burn.
Yes, that's true. That's true. And you haven't finished yet. Anyway, so it's a very, that's a very interesting, now I'm just pure, this is, I think, purely historical. I don't think this would survive to their creators. But anyway, there is something called decoherent histories, which is a clever way done by genius. I mean, one genius, at least Gell-Mann and Omnes and Griffiths and Omnes, but Gell-Mann and Hartle, two teams, which is really interesting because this is entirely based on the ignorance of the no hidden variable theorem that I just mentioned. So the idea you assign probabilities to sequence of events, which are defined by events that occur in the world, but independently of measurement. So they want to have a sequence of events, then sometimes you may measure, and then you find that result, but you know, these things occur. But of course, they want to define probabilities to these histories, but there will be inconsistencies because of interference. If you take the famous double slit experiment, you can't say that the probability being on the second screen at the point X is the sum of the probability of going through one slit and ending that, and going to the other slit and ending at the same point. So you have to make sure that your histories are what they call decoherent, which means essentially that you can assign probabilities because there is no interference, and basically it reduces to introducing measurements without having measurements. But anyway, the idea, the philosophy is nice. Okay, they want to give probabilities to histories of real events in the world, but they are defined, that's their mistake, defined through arbitrary observables. And then they run into problems. Because they do not are aware of the problem posed. Of course, nobody is aware of these no hidden variable theorems. And Goldstein on the one hand, and Bassi and Gherardi on the other, have shown that you run into contradiction, even if you consider history as a quotation mark at a fixed time. So there's no problem of, there's no problem of interference, but you can run into a contradiction. Just you take histories, or events at a fixed time, that are each equally valid from a decoherent histories, namely each of them correspond to a real event in the world. There's no reason to choose one or the other as being really real, okay? But taken together, if you take all these histories together, you run into a contradiction. So you can say, okay, now they can't all be true, so which one is true? But by symmetry, there's really no reason to choose any of them. So it looks like your theory is running into a contradiction. The lesson is simply that observed eigenvalue of operators are not values of the physical system under consideration, but rather a result of genuine interactions between the system and the measuring devices. The proponents of the decoherent histories do not seem to have accepted this, even after it has been pointed out to them by Goldstein, Bassi, and Gherardi. And I must say, Robert Griffiths, whom I wouldn't say I did my thesis with him, but I did when I did my thesis, and this Chuck must remember that too. I use Griffith's inequalities and work in statistical physics, but he has been absolutely stubborn in his discussion with Goldstein about this and with me. So they really don't get the point. Anyway, paradoxically, what they ignore is something that Bohr said, and it is correct, but it's said vaguely. He said that it's impossible to make a sharp distinction between the behavior of atomic object, the elementary particle, and the interaction with the measuring instrument, which serve to define the condition on which the phenomena appear. In other words, they commit the sin of what Dirk Goldstein Zange calls naive realism about operators. Namely, they think that eigenvalues of operator correspond to real properties of the particle and not, as I will show in the Broglie-Bohm approach, the result of interaction between a measuring device and a particle. Okay, now I'm going to come to the three theories which you may be more familiar with, or maybe, I will go in review: spontaneous collapse, many words, and the Broglie-Bohm. Okay, so the spontaneous collapse, the idea is you have Schrödinger revolution, and then you have this macroscopic superposition, but it does not survive more than a split second. The idea was introduced by Gerhardi, Rimini, and Weber, and subsequently extended by many people, but I won't go into the details. So the original idea is that the wave function evolves according to Schrödinger equation, but there is a set of space-time points chosen at random, so that the wave function for a system of n particles is multiplied at the chosen time by a Gaussian function, the variable xk, chosen at random, centered in space at the chosen space-time point y. Okay, so you multiply by a Gaussian, and the Gaussian localized part of your wave function. But if you have a wave function of a cat alive and cat dead, if the wave function, some of the wave function of the particles of one of the two is multiplied by this Gaussian, then it collapses the whole wave function, basically because a product, these wave functions tend to be product of wave function for each particle, and if one particle gets localized, then the whole wave function gets localized because a product of okay, I'm sorry, I go ahead. The probability is determined by the chi-square distribution, so the prediction will be almost coincide with the usual one, but not quite. Okay, and then of course this localizes the wave function, and for a system of many particles, they collapse the quantum state into one of the terms, either psi cat alive or psi cat dead, because a product, even if one of those wave function collapses to zero, then the whole product of wave of factors, one of which is zero, is equal to zero. That's trivial. Now the trick, because it's a trick, is to choose the parameter of the theory so that spontaneous collapses are rare enough for a single or for a few particles in order to ensure that they do not lead to detectable deviations from the quantum prediction, but are, of course, detectable so far, but are frequent enough to ensure that a system composed to a large number of particles will not stay in a superposed quantum state more than a split second. So it's not the same as ordinary quantum mechanics, since they do lead to prediction because of the collapse that differ from the usual one, even for a system made of a small number of particles, but the parameters are simply adjusted so as to avoid being refuted by present experiment, and I say which is not exactly an appealing move, and you don't have to be a strict Popperian to argue, accept that statement, okay? Moreover, and that's the other problem, is the problem of making sense of the pure quantum state. You see, you have, as I said, the wave function of the cat alive, the wave function of the cat dead are not objects in 3 dimensions. And two solutions, so you want to link this function defined in a high dimensional space to things in R3. And then two solutions have been proposed, the so-called matter density ontology and the flash ontology. So I call it GRWM and GRWF. They have not been proposed by GRW, but anyway. The continuous matter density is simply that is associated to a wave function by the formula like this. What you do is you integrate over all the variables, fixing one of them to x, then you integrate all the variables, and then you sum of all the variables, the masses of the corresponding variable, and that's the usual wave function. There are many reasons why you could like this formula. I will explain why I don't like it, but anyway, it sort of associates the wave function now a matter density which is distributed continuously in space, in the real space, and so this object which is defined on R3n now is associated with an object defined on R3. Okay, and that could be a cat, which is allowed for that.
So you might have just said something about this, but the wave function itself is part of the ontology on the space.
Yes.
And it doesn't exist in three-dimensional space.
Yes, that's what I said.
I just said, I think, just to say, but I didn't understand how the mass distribution then does exist in three-dimensional space and how it's connected to the wave function.
But you have to look at this formula. You see, m is a function, x is in 3 dimensions, and there you integrate over whole variable, fixing one of the variables to be equal to x, and you integrate over the other variable. Okay, just replacing that argument xj by x, that's what the delta function does, and then you integrate over the other variables.
So is the mass density is an additional bit of the ontology, it's not just the wave function.
You're jumping ahead of me if I want.
Okay, sorry.
No, that's okay, it's okay, but I'm just saying yes, what I mean. So you have but of course you have to see what it means, okay? You have to be concrete. It means that in a three-dimensional world, it's just a continuous density of mass. There's no structure, no atoms, no molecule, no brain cells, etc. Just an amount of stuff with high density in some cases and low density elsewhere. In the Flash ontology, it's even more. I think you will find many things surprising, Chuck. The world is even more bizarre because the world is only made of the space-time point at the center, which are the center of the Gaussian that collapse the wave function. So the world has no particle, no field, nothing, except a galaxy of space-time points called flashes. It's empty. It's empty most of the time because there have been in the visible universe in the Big Bang, there have been only finitely flashes. And so most of the time, the whole universe is empty.
You use Gaussian multipliers for convenience, or?
Oh, that's a good question. I see the mathematician here. Yeah, because they always say, oh, we adjust the two parameters, the frequency of the collapse and the size of the Gaussian or something like that. That's not true because there is a whole space, a Hilbert space, or not even a vector space or function that will do the job. So you could take any Hermite polynomial, and then in reality, you fix an infinite number of parameters equal to 0 by choosing a Gaussian. I didn't say that, but that's a good point, yeah. But now, if either GRWM or GRWF is true, then to take the famous sentence of Einstein that God is subtle but not malicious, God must have been very malicious. Because in GRWM, we're all wrong all along when we discovered atoms, etc. And we're lying to school children saying that matter is mostly void with a few pieces of matter, the atoms here and there. Indeed, matter is continuous after all, with higher and lower density in some places, and we have been simply fooled by that version of quantum mechanics into thinking that it is not. And if the Flash ontology is true, then we have been fooled into thinking that there exists something most of the time. If we take the visible universe since the Big Bang, as I just said, it has contained only finitely many flashes. So flashes are all there is. This means that most of the time, the universe is just empty. Because, okay, I'm talking about taking the time to be continuous, of course. Anyway, I want to say that, of course, you might be forced to accept that, like we were forced to accept atoms. But the big difference is that if it's more explanatory or greater empirical adequacy. And this is the most important point, empirical adequacy of the spontaneous collapse theory would mean that ordinary quantum mechanics is empirically wrong, at least for a small number of particles, since the prediction of both theories differ at least in principle, and the difference is just made difficult to detect because of the choice of parameters. So If one finds that the prediction of a spontaneous collapse theory is right, where it differs from ordinary quantum mechanics, it will be a major revolution in physics, and you might be forced to worry about those weird ontologies, but this hasn't happened yet, and I would suggest not to worry about what to do after the revolution before that revolution has occurred. And I was talking to Shelley Goldstein, I was staying with him the last few days, and of course he pointed out to me that if you found such a violation, it could be because of the effect of some unknown particles that may have an effect on the effective wave function. I don't want to go into the details, but you could find many other explanations. And I don't think if that happens, the physicists will jump, oh my God, we forgot that this is wonderful theory with ad hoc parameter, continuous matter density, or flash ontology, and so on, and that's going to solve all our problems. No, they're going to look for another theory. That's certainly not one of those, and that's why I call it non-Newtonian years, because Roderick Tumulka, who many people know, was a student of Detlef Dürr, and recently he said that they asked him when people will accept the Bohmian mechanics, and he said 1,000 years. And I say this will not be accepted even in a million years. I don't know if he's so pessimistic. Anyway, I won't be there to check. But I still want to emphasize, and I think it's pedagogically useful, to see how odd those ontologies are compared to a particle ontology of the Broglie-Bohm theory, to be discussed later, but in that ontology, they're just particles and they move, okay? Consider a thought experiment, which I think is very interesting, the Einstein boxes. You imagine a box containing just one particle that is cut into two parts. One is sent to Paris and the other to Tokyo. I had to change my slide because when I do it in Europe, I say one part is sent to New York and the other to Tokyo, but that doesn't work here. So I cut it into two, and I send the wave function for the party. The wave function is simply a superposition of a wave function located in B1 and a one located in B2. In ordinary quantum mechanics, when Alice in Paris opens her half box and sees the particle, the wave function collapses on the part of the wave function located in Paris, and she doesn't see the wave function collapses on the part located in Tokyo, which is, of course, a bit funny. But of course, if you think that there are not only the wave function, but also the particle, then of course, nothing really surprising happens. But now, in the GRWM theory, there is one half of a particle in each box because it's a continuous matter density. And when you open one box, the matter density jumps either from the other box to your box or from your box to the other box to make a whole particle. Okay? And so there is a non-local transfer of matter in GRW theory, and they of course know such thing and nothing non-local when you deal with only one particle. In the GRW with the flash ontology, there is nothing in each half box because everything is empty. But when you open the box to look for the particle, then suddenly there are lots of flashes in that box, and then the flashes can be either interpreted as the particle being there or the particle not being there, and then you have flashes in the other box. And so you're creating flashes at a distance. It's a bit. So putting aside the weirdness of the ontologies, the spontaneous collapse theories are more non-local than what happens for two particles and what EPR and Bell have shown must exist. You have a non-local effector action at a distance, even for one particle and very radical way. So in summary, they have unnatural ontologies, to say the least. They are very ad hoc. Moreover, recent results, but that you have to check, seem to provide evidence refuting those theories, but that's under discussion, of course. They can only be true if quantum mechanics itself is false, and they're more non-local than they have to be. So, okay. Now, the many worlds. The naive view is that when the proverbial cat or any other macroscopic device is in a superposed state, then instead of having a collapse by fiat, as in ordinary quantum mechanics, both terms seem to continue to exist. Okay? But then, of course, they exist, but in different worlds. So if I still think naively, whenever an experiment leads to such, the world split into two or more worlds, depending on the number of distinct macroscopic states produced by that experiment, one world for each possible result. This means that not only my brain and thus my consciousness, but every molecule in the universe is copied twice. But that is another, maybe not instantaneous. I mean, you think of it that there are certainly many laboratories in New York, but also in Europe, everywhere in the world. And each time there is an experiment, there are copies of us that get multiplied, which is a little weird. But anyway, it's interesting that in his original paper that was invented by Everett in 1957, he said that all elements of a superposition, so all these branches of catalyzed, etc., are actual none any more real than the rest. He felt obliged to write this because some correspondents had written to him saying that since we experience only one element, why do we assume that these other exist? This shows that some early readers of Everett were baffled by the radical nature of the many worlds proposal. So I want to show that there is a deep problem, which I learned from Tim Mordin. I mean, I hope you will agree with me at least, about the Born rule. Suppose that the probabilities of having cat alive and dead is 1/2, 1/2. Okay, I make an experiment where the results are symmetric and so on. And I decide to repeat the same experiment successively with different particles, but all in the same state and different cats. After one experiment, there are two worlds, and one world where I see the live cat, the other I see the dead cat, etc. Okay? Then I repeat, since the copies of me are in the same state of mind, I repeat the experiment. Then you have 4 worlds with 2 dead cats, 2 live cats, and 1 dead and alive, and then you have 8 worlds, etc., etc. Now continue repeating the experiment. So some of my descendants, by descendants I mean the copies of me in all these worlds, it's a bit crazy, but let's continue, that will see that sequence of events. So there will be a sequence of worlds where the cat is always dead, one is always alive, and then there will be many ones where it's 3/4 of the time one, 1/4 of the time the other, okay? Any statistic different from 1/2, 1/2, and this is also true what I call my cousins, namely descendant like me of some of our ancestors that live in those other worlds if the experiments are done, okay? So of course there are lots of people in my descendants that won't see the Born rule. But you could use the law of large number, or what people call typicality, to say that in the vast majority of worlds, the Born rule will be applied because of the law of large number, the frequencies will be close to 1/2, 1/2. But what happens if the quantum probabilities are, let's say, 3/4, 1/4? You still have 2 worlds because the structure of the multiplication of the worlds is exactly the same. You just have 1 world for each macroscopic outcome. And so you get exactly, but now the law of large number, of course, implies that the Born rule, 3/4, 1/4, won't be observed. It will be still you will still be 1/2 cat alive, 1/2 cat dead. So you won't see the result of the Born rule. Of course, that's a very serious problem. I think they don't agree, but some authors, like Everett, and many others, even Shelley and others, have argued that one should count the world differently by weighting them with the coefficient that appear in the Born rule. However, this is an instance of Gigot. I don't know if you philosophers use this garbage in, garbage out. The goal is to explain where the Born rule comes from in a deterministic theory, not to oppose it from the start. You see, I don't think you are free to put the probabilities as you like, because I have my experiment, I give you the frequencies, and your probabilities should explain the frequencies. If the frequencies disagree with the Born rule, you can't put probabilities that will agree with it a priori. Another solution is to give low probability worlds. For example, if it's 3/4 and 1/4, then of course there will be lots of worlds where it's half of the times 1/4. But of course, the problem is that those worlds will have smaller coefficients, will be 1/4 to the power n, etc. So they will have smaller coefficients, and you say they have a lower degree of existence or of reality. But it's unclear to me what it means to live in a low reality world, since the world is exactly the same structurally as our world, okay? And the world don't interact with each other. You can't go, hey, I'm going to see in the 3/4, no, because there is decoherence, so the wave function don't interact. And of course, it's contrary to Everett's original idea that all elements are actually none more real than the rest. And then you see, I think it becomes incoherent because to me, if something exists, it being existent, simplicity. I cannot review all the solutions, and they are discussed in Tim's book, that have been proposed since 1957, because they realized the problem back then, to fix this problem, including betting strategies, rational decisions, so on, that I don't see what they have to do with physics, because they bring in human agents again. But it seemed to me that the natural conclusion is simply that the many world approach is not empirically adequate. Okay. Now we go to the real thing, the beauty of the Broglie-Bohm's theory. I first have adapted a little bit what Alexander Pope wrote about Newton. Nature and nature is law, lay hid in Copenhagen. God said, let the Broglie-Bohm be, and all was light. I mean, okay, some of you may know what Pope said. Nature said, nature's law lay hid by night, but God said, let Newton be, and all was light. That's. I will not give the detail of the theory, but for a system of n particles, the complete state is a pair where psi is the usual quantum state and q are the actual position of the particles. So particles have position, they evolve in time, contrary to what you have been told. And the quantum state evolves the usual way. It never really collapses, at least for a closed system, and it guides the particle. The velocity of each particle is a function of the wave function at that time, evaluated on the position of all the particles of the system. Since Barry said don't put too many formulas, I just say it's a function, the k coordinate evolves as a function of psi, and what is of course special is that it evaluated on the actual position of all the other particles, and that of course I could explain it more, but that shows the non-local nature of the theory. But I won't go into that unless we discuss, okay? So here there is a very famous numerical simulation of the double slit experiment, where you have the double slit experiment and you send particle, and each of the wavy line is a possible trajectory. And this is just a numerical solution of the equation of motion. So you send the particle here, they are starting point, but there are too many of them, you can't distinguish them, but each of them give rise to a wavy line. And then you can see that here, it so happens that there are these interference patterns. Many particles here, very many particles here, almost no particles there. So you see exactly the interference pattern being reproduced. And what happens is that the wave function, the particle goes through one hole, which of course makes sense. The wave function goes to the both hole because the wave, that makes sense also. You can think of like, water, a little boat going through those holes if you wish. And then after the holes, the wave function guides the particle, but of course the wave function is affected as to whether both holes are open or not. And then there is also what we call a nodal line here, that because it's symmetric, the particle cannot cross. So in fact, you can, by detecting the particle here, tell through which hole it goes, if you believe the theory, of course. And notice also that this is a motion that does not respect Newton's first law. Because you see, Newton's first law said the trajectory of straight line in vacuum. Here there are no force. The only thing that acts on the particle is the wave function. But who tells you that quantum mechanics should be like classical mechanics? We have been told all the time that this changes philosophy and changes everything. So it could at least change the equation of motion. That wouldn't be too bad. But anyway, so now I want to go to the real beauty of the Broglie-Bohm theory, which is it explains what happened during measurements. That's really the thing that seduced me in the theory. Because the measurement, as I say, it's a deus ex machina in ordinary quantum mechanics. And I want to show you how measurements are not measurements. Measurements are interaction between the apparatus and the particle. It's real interaction, and the statistics of the result of this interaction is given by the Born rule, but it's not, it comes out of the equation. So I will consider two examples. One, a measurement that's something that does not exist, the spin, and a measurement of something that does exist, but is not measured by that measurement, the momentum. I think those two examples are very clarifying, and I hope that will convince you. Of course, saying like that, it looks like a superstition, but that's exactly, I will explain what it means. So for something that does not exist, actually, I learned it from David Albert's book. you take a Stern-Gerlach apparatus that measures the spin in some direction. And so you start with a wave function as a spatial part, and the spin part is just a superposition of spin up and spin down. And there's a gradient of the magnetic fields in this direction, and then the wave function, the up part will go up, and the down part will go down. That's ordinary quantum mechanics. That's just standard quantum. Now I do Bohm, or the Broglie-Bohm, and I add the position of the particle. And then it turns out that the particle will go up. It will go up because, so it will go in the direction of the field, of the gradient, and therefore its spin will be up. It will be in the wave function which is up. And it does that because it starts above this middle line, and just like in the double slit experiment, you know, if it's initially in the upper part, it will go upwards. But now repeat the same experiment with the same wave function and the same initial position, exactly the same. So the whole quantum state of the particle is exactly the same. But you reverse the orientation of the field. Now, what will the particle go? It will go up again because it cannot cross this middle line. That's part of the dynamics. But now, of course, the spin will be down. Because now going upwards means going down, going in the direction opposite of the gradient of the field. So the particle whose spin was up will have its spin down, although you measure exactly the same quantity, the spin with exactly the same initial condition, but with two different arrangements of the measuring device. So there is an active role of the measuring device. Another way to say this is said by Shelby and others, spin is not real. Of course, spin is real in the wave function. Spin is part of the wave function, but doesn't have a value of spin which a spin measurement reveals. Or, I prefer to say, quantum measurements, I always have to put quotation mark in measure, do not measure spins, but their interaction. They do not measure something intrinsic to the particle. Now, let me go to the other example, where you measure something that does exist. Obviously, these particles have trajectories, their velocities at all times, because the equation of motion tells you what the velocity is. But if you measure the velocity or the momentum, then you get a result that does not coincide with the real velocity. And the simple example is to take a particle in a box, this box, and so the ground state is wave function is real, and then it turns out from the equation of motion that the particle is at rest. So you know its velocity is zero. And you can measure its position with arbitrary precision. There's nothing preventing you from that. So you know the velocity and the position at arbitrary precision. Doesn't that violate Heisenberg's inequality? No. Because, again, deducing the velocity from the theory is not what you call measuring the velocity in quantum mechanics. What you mean by measuring the velocity, you need to open the box, and you can do the calculation, that's in my book. The particle escapes, it travels a certain distance, and then you divide the distance traveled by the elapsed amount of time, that gives you the measured velocity, and it's not zero, and the statistical distribution of the velocities will satisfy Heisenberg inequality. But has nothing to do with true velocity of the particle before the measurement. So that, I think, is another beauty of the theory you may, of course. And again, this vindicates what Bohr taught, but on the impossibility of sharp distinction, except that now it comes from the equation of the theory and not from some philosophical a priori, which I think was what happened with Bohr. Okay? Since measurements are interactions that do not reveal pre-existing properties of the system, the Broglie-Bohm theory is not refuted by the no hidden variable theorems. Remember, I said it's impossible to assign values. I was confused by that, but you see, you would think that since the theory is deterministic, every experiment will reveal some property of the particle. No, because you have to look at what the measuring device does. And so you are not refuting the no hidden variable theorem, which says you can't assign values to operators. It is a statistical theory because the particle position is random, but it's a consistent one because it does not associate pre-existing values to observables other than position, which shouldn't be taught as an observable. Now, to the conclusions, I think I'm more or less in time. The main reason is why there are no three realist theories, you know, the Broglie-Bohm, spontaneous collapse, and many worlds, is that two latter suffer from extravagant ontologies, if you're willing to worry about them, maybe more non-local that is necessary, at least for the spontaneous collapse models, are either extremely ad hoc and or empirically inadequate for many worlds. On the other hand, the Broglie-Bohm theory is not yet another interpretation of quantum mechanics. It's not different than quantum mechanics. It's simply the completion, what they call the rational completion of quantum mechanics, which is manifestly incomplete since it does not speak of what happens outside of laboratories. And ordinary quantum mechanics is simply the Broglie-Bohm theory applied to what happens in laboratories. It explains what happens in the so-called measurements. So what else could you ask for? Okay. Once this is understood, there is no need to run around in search for alternatives to quantum mechanics or interpretations of it. The Broglie-Bohm theory explains what is going on and allows one to have a clear understanding of the errors or weaknesses of any other approach to quantum mechanics. And I'm going to quote another philosopher, which is not Hume, Verum Index Falsi, which I suppose you know. And I can't help doing some self-advertisement if you want to know more. Okay, thank you.
Discussion. Okay, I'll run discussion.
But please, let me get something to drink, some water.
Yeah, you get some water right down.
Because I'm very thirsty.
It was a tour de force.
Where is the water?
Who has questions? Jacob had a question. I'll keep Jacob.
Thanks, Barry.
Jacob and who else is? Matthew. Other people on my list of questions. David, any questions?
David who?
Oh, you. Do you want to be on the list of questions?
I'll see. Me too, I'll see. How the previous
Okay,
question
okay.
go.
I have a question, so maybe they'll come to me as fourth.
Okay, now start the battle.
Okay. So we deal with questions. So Jacob goes.
This is a wonderful talk.
Thank you very much.
Thank you. So depending on exactly when you date the beginning of what we think of as the Copenhagen interpretation,
Sorry?
depending on when you date what we think of as the beginning of the Copenhagen interpretation, I'm not sure there's a strict date. I know that Heisenberg, wrote a chapter in his book on the Copenhagen interpretation, but that was 50s, but certainly he was reflecting views that came before it. Bohmian mechanics, Bohm is working in the early 50s, but de Broglie was already working on it in the 20s.
23.
23, right?
We made a conference in the French Academy in 73 for the 50th anniversary, which was quite obviously referring to his own work, because at that time nobody else was doing that. He did his thesis in 24, but he wrote some notes to the French Academy in 23.
Right, and then of course Everett goes back to the mid 50s, right? His short version of his PhD thesis was 57, but he had been working on his approach by 1956.
Okay.
Yeah. So at the upper bound these triumvirate of these three famous interpretations of quantum theory, not including spontaneous collapse approaches, which came later, had been written down, and to a good approximation in a form that we would recognize today, 70 years ago. So I guess my question is, there are good reasons that you've explained for why some of these interpretations haven't caught on or haven't, convinced physicists or haven't reached a consensus status. But I have to say that in my view, there are also some reasons why de Broglie-Bohm hasn't caught on, and it's not merely historical prejudice. So the standard de Broglie-Bohm approach has somewhat complicated laws. They're not too bad, but they're a little bit complicated, right? You've got the Schrodinger equation, that's fine. You've got the guiding equation. Of course, the guiding equation on many readings entails a preferred foliation of space-time, which is a little bit unnerving, but whatever. You do need the initial equilibration hypothesis in order to get things off the ground.
Okay.
It's already a little bit complicated.
I should write down all the objectives.
Sure. But that's not maybe so bad. I mean, after all, if it gives us a beautiful picture and it does all the wonderful things that you're saying, which it does, it's great. Maybe that's just a bullet we have to bite. But as I see it, the biggest problem with the de Broglie-Bohm approach is that no one has been able to find a satisfactory generalization of it beyond systems of finitely many non-relevant particles. Of course, work has been done over the last 70 years trying to generalize it. I am not the world expert on generalizations of Bohmian mechanics, but I've read a lot in the literature on it. And the generalizations tend to be much more complicated. They often give up the determinism that makes the Bohmian approach in many ways very attractive. They don't handle fermionic quantum fields very nicely. And even to the extent that you can kind of fit something like a Bohmian type framework to contemporary, cutting edge physical theories, quantum field theories, systems of abstract qubits, string theories, what have you. They get extremely complicated and they begin to look like exercises in curve fitting.
What in curve?
In curve fitting, like you already know what you want and then you just design bespoke laws until eventually they fit. Personally, this is one of the reasons why, although I'm probably more partial to the de Broglie-Bohm approach than any other interpretation, this has been my obstruction to taking it on.
I've heard that before.
So I guess my question is, it's been 70 years. Why don't we yet have a satisfactory generalization of the de Broglie-Bohm approach to our most empirically successful quantum theories like the Standard Model, let alone more cutting edge speculative theories like you find in string theory or EDS, CFT, or what have you? So I guess that's my question. Why don't we have it if this is really the way to go?
Yeah. Okay, there are many different things. Let me start with Copenhagen. You see, the problem is there are several, you must be aware of that, and maybe Tim can help me remember who wrote these things, but there are several articles saying that there is no such thing as the Copenhagen interpretation. There is something which is taught in textbook, which comes from von Neumann and Dirac, which include the collapse postulate, and it's not explained. And again, if you really go to the bottom of it, it's a theory of what happens in laboratories and not what happens in nature. And I was bothered when I was a student by that, because we were told that, oh, we don't speak about nature, but about our knowledge of it. But that's silly, because if we have knowledge of nature, then we speak about nature. I mean, the self-contradictory sentences were repeated ad nauseam and doesn't make any sense. So Copenhagen is still the dominant so-called interpretation, although when I go to conference, I've been to many conferences, nobody defends it anymore, but it's still what is taught in classroom. So if the Broglie-Bohm has not caught on, you could also ask yourself, if it's not due to prejudice, then you could ask yourself, why has Copenhagen survived so long without no prejudice? It seems to me that this is very much an example of prejudice, that people repeat these things all the time. And as I say, I mean, Bohr has his view, Heisenberg has his view, Pauli has his view, Jordan has his view, and Dirac probably, and probably von Neumann, to all these people, if you really, I won't go into the exegesis of these texts, but I've been through these texts, and obviously they don't mean the same thing, and in the end, it's not clear what is meant. Okay, so committed to the flames. Now, but of course, it's a big, big place to burn, many things to burn, because you can put all the textbook of quantum mechanics throughout the world. That's make a good fire. Anyway, so then you have the question of quantum equilibrium. You must realize that in any dynamical system, there must be assumption on the initial conditions. And in any, for example, if you do scenario Bohm measures, if you do dynamical system, etc., you always have to study, put some assumption on initial condition. You do it in quantum, you do it in statistical mechanics, you do assumption on initial condition that out of equilibrium. Here we have something which resembles equilibrium, called quantum equilibrium, which is in some sense natural. But you cannot have a deterministic theory without assumption on initial condition. So it seems to me that this is actually quite natural. The preferred foliation, well, you're certainly such an expert, because I know your seminar at Harvard, that you must certainly know about Bell. And Bell shows that the world is non-local. So if you want to maintain the ideas of cause and effect, then you have to have a preferred foliation. If you don't want that, you can do block universe, you can do what you want, you can do other things. But to use a sentence of Tim, choose your poison. You see, either you abandon the notion of cause and effect, or you have to put a preferred foliation. And I was just discussing with Chelly, he has a scheme which is not developed yet to introduce preferred foliation independently of quantum mechanics directly in relativity. I don't know if that can work, but it seems to me that the preferred foliation has nothing to do with Bohm. I mean, the reason we have to introduce it. Moreover, once you realize that the world is non-local, which is what EPR Bell shows, then of course, one of the main objections to Bohm, which is that it's non-local, goes away. Okay, I just saw a student, I was talking in Paris a few weeks ago, and I saw a student, so I always thought that Bohm is out because it's non-local, and now you convince me that this is an objection. Okay, now we go to the question of quantum field theory, arbitrary number of particles, etc. Well, it so happened that I gave a talk yesterday at the Rutgers Conference of Statistical Mechanics about a friend of mine who had been working on quantum field theory from a rigorous point of view. And so I had to remind myself of what the results were there. And you see, the problem is that many physicists say, oh, but maybe there are no particles, there are only fields. But then they commit naive realism with respect to fields. Okay, maybe there are fields. I mean, you can have a field ontology. Even Bohm did that in 1952. But that doesn't, I don't think why that solves any problem. And the problem of quantum field theory is that it's extremely difficult to make sense mathematically of the ordinary quantum field theory, number one. Number two, I challenge you, maybe you will send me an email about that, but I challenge you to find a book of relativistic quantum mechanics, quantum field theory, and blah, 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 that contains words like collapse of the wave function in the index. The problem, yeah, but it's a problem, because when you study quantum mechanics, they say, oh, there is a list of axioms, blah, 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 and then there is the collapse rule, always. And then you go to the so-called extension to relativity of quantum mechanics, which is quantum field theory, and then the axiom has disappeared. Oops.
To be fair, often when they compute S matrix elements and compute absolute value squares, I definitely hear people talk about, okay, and then the plane wave collapses at the detector. So I do hear people say that.
Yes, yes, but the problem is, of course, and you know, yeah, but you know very well why they push it under the rug. It's because the collapse, ordinary collapse for entangled pairs, just stupid entangled pair, nothing to do with quantum field theory, is non-local. And therefore, it's not easy to deal with relativity unless you introduce a preferred frame, which they don't want to do. So people say, oh, but we don't need non-locality because we have quantum field theory. Quantum field theory is local, something which is discussed by Bell, by the way. But it's not, because it never deals with you know, the entangled pair. So yeah, I'm coming to that. Don't worry. But you see, they never deal with that. And so it seems to me that it's simply not true that there exists relativistic extension of quantum mechanics. There are fields theories, but the field theories, as you say, they compute from minus infinity to plus infinity. And then some physicists at Rutgers say we should worry about what happens in between, and then everybody was upset with them. So they seem to be that there must be something before alpha and omega. I mean,
Well, but there are rigorously defined quantum field theories in 1+1 spacetime dimension.
oh, more, even in three. I just gave a whole lecture yesterday on that. I know several. I mean, it's also, you can also do it in 4 dimensions. You can do all kinds of.
For sure, there's conformal field theories that are even complete. All
No, but not even conformal. I mean, really constructive when it's not.
Sure. But why don't we have satisfactory de Broglie-Bohm pictures for those theories?
Because it's already, but first of all, we have, number one, we have various, I mean, if you look at the work of Dürr-Goldstein, well, first of all, it was already in 52 in Bohm. You can have.
He was dealing with Bohmian, with
bosons.
With bosonic field theories, fermionic field theories.
And then there was several proposals of Bell, and there are proposals of Goldstein, of the Dürr-Goldstein and Zangi. There are several papers which I'm not familiar. You can read the thesis of one of my compatriots, Ward Strive.
I'm deeply familiar with his work also, but none of them deal with fermionic quantum fields in a satisfactory way.
No. You can discuss fermionic particle theories.
You have to either bring back particle ontologies, but in sort of a hybrid way, where you treat the bosonic fields as
yes.
But it. Like
so what? Said, so what? I mean, why? I mean, you seem to say, okay, there is this formal theory which is okay, but it's not okay. It's not okay mathematically, unlike ordinary quantum mechanics, which is okay mathematically, and it's not clear what the ontology would be. For us, it's not clear, but that's a problem. I mean, nature is in some sense hidden. I mean, we have to find out which ontology is the best, and mathematically, it's not easy to work with. And you say that we have abandoned determinism, but that I don't really care. I mean, I don't find that the Broglie-Bohm is attractive because of determinism, just because it speaks about the world outside of laboratories. That's what I want to know. I want to know, have a picture of what goes on in the world outside of laboratories.
Would you be satisfied with something like de Broglie-Bohm, but maybe with different laws? But that's general enough to accommodate more general kinds of systems.
So, I mean, I will have to look at the laws. I mean, I can't tell you like that without consulting my lawyer being reminded.
Jacob, do you think you're
yes.
person?
Yes.
Okay.
We should.
Okay, so Matthew?
I have a finger, just on, do we have fingers in this?
Do you have any finger?
I have
see one. As long as it's that finger, it's okay.
I mean, we do have reason to believe now that we might be able to formulate GRW type theories in a Lorentz invariant way.
Yeah.
So it doesn't seem quite fair what to say it's no to speak as if a preferred Lorentz frame is something we know to be inevitable from Bell. It's not true. We have non-locality in these GRW.
I was going to, that's a great point. Yeah. Non-locality doesn't necessarily, there's actually distinction. And Wayne Mervold has a really beautiful paper, a no-go theorem from 2002, where Wayne Mervold has a beautiful no-go theorem where he makes a really beautiful distinction between non-locality and he proves that a certain class of modal interpretations are not merely non-local, but actually single out. They are somewhat different concepts, non-locality and preferred.
I really, okay. I
think away because Matthew.
Yeah, but okay, just maybe you have a better answer, but my answer is that as I try,
As I'm in charge.
as I try to explain, you see, the problem with GRW is that it may be Lorentz invariant, but it's more non-local than it has to be, even for one particle, which I find really extremely weird. I must confess that I discussed, of course, with Tumulka and with Dalia Alori, who is also working on that. I don't really understand where how does this Lorentz invariance come from? That's true. But it seemed to me that in a deterministic theory, you will have a preferred frame. And it seems to me that in their theory, there is simply no cause and effect. You see, in ordinary quantum mechanics, if Alice makes an experiment, then she reduces her wave function, but also the one of Bob. That's the non-locality in ordinary quantum mechanics. You could say, well, that's because it's information and so on, and then you're led to hidden variables, and these hidden variables don't exist because of Bell. So you are back to the fact that the collapse of the wave function, or whatever replaces it in your favorite theory, will be, in some sense, non-local. And so there will be either there are no. It seems to me that in GRW there are simply no cause and effect. And of course, if you take a block universe point of view, then there are no cause and effect either, and therefore, well, maybe the theory is Lorentz invariant. I just say that if you want to maintain the notion of cause and effect, then you have to have a preferred field. But Tim has a better answer for it.
Right, so first, thanks for the talk, I enjoyed it. I have to leave in about 5 minutes, so I may not be able to stay long to discuss. I actually was going to ask a rather similar question to Jacob, namely, I'm a physicist, I'm not a philosopher, and the way that quantum mechanics is used now in 2023 is not to describe systems of n non-relativistic bosonic particles, it's to describe superconductors, it's to describe
what?
superconductors, topological insulators, many body localization,
NV centers.
NV centers, quantum fluctuations in the early universe, quantum information, quantum computation. None of these systems have, or very few of them have much to do with n particles moving around in 3 dimensions.
No, that's not so simple.
So I think one reason why de Broglie-Bohm has not taken off in the physics community is that it just doesn't describe the systems that are to which quantum mechanics is being applied. And so, I think if you want that interpretation to gain credence in the physics community, that's really where the effort needs to be focused. It needs to be shown that this pilot wave interpretation makes sense when you're talking about spins in a lattice, or when you're talking about all the systems I just mentioned. So, if it does, it's not known to me, and I don't think it's known to most physicists.
Well, the problem is that the way.
The relativistic side is, I think, even more a severe question. I mean, I absolutely don't agree with you that there needs to be a preferred frame. I also don't agree that Bell shows that quantum mechanics is non-local. I think that's the standard view among physicists that study relativistic quantum field theory. So I think, again, I mean, if you want to make headway there, you're going to need to show that you can explain why the world is Lorentz invariant to incredible precision, right? You can explain why at particle accelerators we can make predictions that are accurate to 10 significant figures. I mean, you're sort of coming up against what is in many ways the most successful theory in the history of science. It has an incredibly broad application to so many different phenomena, and it makes extraordinarily precise predictions for specific phenomena. And none of those phenomena, or very few of them, are addressed in de Broglie-Bohm. So I think that's fundamentally the reason why physicists just don't pay a lot of attention to it.
Okay.
And so I'm just saying, I think that's where you need. If I were you and I wanted to convince people that this is the right way to go, those are the kind of questions that I would start with. Not criticizing all the other interpretations for their failures, but showing that this one actually works.
Well, first of all, then, okay, you don't have only to read my book, but also Tim's book on non-locality, quantum non-locality and relativity, because I think, also it's discussed in my book, I think the EPR Bell argument showing that the world is non-local seems to be extremely convincing, but if you have to leave in 5 minutes, then I can only give the argument after you have left. But
I know the argument.
yeah, okay, you not agree, so you have to agree to disagree. But the point is that okay, for these other things, you should not go too fast, because you see, in the end of the general scheme that has been developed mostly by Leo Goldstein and Zangi says that in the end of the day, in the de Broglie-Bohm, I mean, first of all, in all the things you described, there are particles. I mean, the quantum, the superconductors and all these things, there are particles. And in the end of the day, the quantum prediction, at least at a given time, will be recovered in the Broglie-Bohm, or in Bohmian, they will call it Bohmian mechanics, or in Bohmian mechanics. But that you have to study what is called equivariance, and you have to study how macroscopic results occur. I mean, I gave you 2 examples of why macroscopic measurements are not so simple, and they explain what is going. It explains what is going on in the Broglie-Bohm theory, and I think maybe no. I mean, I still maintain that the problem is due to prejudice. I mean, after all, the EPR 35 paper is the most quoted paper by Einstein, of course, there are 2 others now, of all these papers. but it took 30 years before Bell really understood it, and nobody paid any attention at that time. And still in the popular literature in the courses, people, oh, but Bohr answered EPR, but go read Bohr. I was shocked by that. I read it a few weeks ago because I had a conference in Paris on that, and I was really shocked to see that it doesn't address the question of EPR except in 2 paragraphs which are maximally confused, and yet everybody is convinced. So just that. Let's not discuss the Broglie-Bohm, just discuss EPR and the response of Bohr. If everybody is convinced, that just means that people, it's a naked emperor business. Everybody is repeating that Bohr is right, but they don't really read him and don't really understand the argument because it's honestly ununderstandable. So I strongly believe there's an enormous amount of prejudice in the physics community, not just against EPR, not just against the Broglie-Bohm, but against all these questions. Don't bother me. Leave me in peace. Shut up and calculate. And all these reactions I've had all my life. And also then, once you go to pure EPR, Bell, and so on, you have a whole web of confusions, and you have to dismantle it without talking about the Broglie-Bohm. Now, I think once you understand the Broglie-Bohm, I think what you have to understand is, I mean, it's not in my lecture that I explain everything. I think once I understand it, the beauty of the theory should be striking. That of course. Anyway, you wanted to say something to Albert.
Matt. Cleveland. Oh, it's nice to meet you. I'm Jacob Veritas.
Nice to meet you too.
Yeah.
You
I have some
wanted to,
follow-ups to.
you wanted to.
Tim, I'd love to listen to them, but I've got
Okay, thank you for coming.
Tim, so I just wanted to come back to David's family.
Thank you.
Thank you.
This very common rhetoric that I think people would take a second to reflect on, which is to say, oh, it's very unpalatable to give up, to put in a preferred foliation. Somehow, this is a big price. We should be worried about this. We should resist. And just think historically. Why did you believe it in the first place? Well, you start with special relativity. What was special relativity designed to reproduce? Maxwellian electrodynamics. Is Maxwellian electrodynamics a theory that will violate locality? No, it is not. Then you go to general relativity, all right? Now you add on something that's going to get you something pretty close to Newtonian gravity. Will Newtonian gravity violate Bell's inequality? It will not. So, I mean, first of all, if you're going to GR, you're not even talking about Lorentz invariants or any Lorentz frames for their heat. But just put it in terms of, is it unpalatable to say there might be a preferred foliation? Well, the theories which don't have one are theories that were not passed to explain concrete, actual, extremely surprising results, namely violation of Bell's.
Tim, I didn't see myself as expressing a position on the
Well,
palatability.
Same. Also, I don't.
John
No,
was
right, it
making a
shouldn't be
logical.
impossible. Yes.
John was
I
making a
agree.
logical point.
Yes, we agree.
Okay.
I don't think you can say it's impossible.
Right.
But I don't equally think it should be thought to be so massively undesirable.
Fair enough.
When you think about where your attachment to the thing came from in the first place. Yeah.
You know, I want this conversation to keep going. So mine is much more rudimentary. So we should.
Just come back. I'd love to. You should.
Well, you know, I'm very new to to Broglie-Bohm. So let's just back to basics for me if you don't mind. You showed the oh gosh, what was the experiment with the magnetic field?
Yeah.
Stroke
Right. So one of the classic examples of Stroke is where you set up 3 in a row, where you rotate it in the middle dial. So can you step through and explain why the Broglie-Bohm gets the same experimental result? Like, why is it that?
Because there is a middle line that they cannot cross, just like in the double slit experiment. But that's just.
What does the middle line mean? You're saying that there's a particle position.
No, there is a middle in the middle of the experiment.
Okay.
You see here, if the thing is symmetric, of course, that would be perfectly symmetric.
Right.
This line cannot be crossed.
Okay.
Exactly like in the double slit experiment, I thought I'd put it back, okay, here. You see this? I think just because the mathematics is that the particle is, how can I say, it's given by the gradient of the wave function. If the wave function is symmetric, then at the point of symmetry, the gradient is 0. So you have an even function on the line, then the derivative
Sure,
at
okay.
0 is 0.
And then so when I take my next gradient magnetic field, I rotate it, then there's another symmetry, that's a different symmetry, and then if it's one or the
Yeah,
other.
but it's still the same symmetry spatially.
The plane is moved.
The planes move, the
Plane
planes
is
rotate.
rotated.
Right, so it's at some point on there, the break, and it chooses one or the other. Right, if it's above, it goes up, if it's below, it goes down. And then the next one, it's either above or below that plane. Right, so it picks one or the other, but then when it goes through that apparatus for the third time, it's still above.
Ah, that's a different story. I'm taking several repetition of the same experiment.
No,
These are not supposed to be
Consecutive,
sequential.
they're not
No, I
sequential.
understand, I'm just asking, because in one of the famous examples of Gerlach, you have three gradient magnetic fields in a row. There's a middle one which is rotated.
Right.
And then you get the third one, which
Yes.
is the original one back again.
Yes.
And the point is that you show that you get half the.
Yes.
Oh, yeah, yeah,
Bohm
that's-
is going to give you that.
That's a different thing.
Okay, right, so I assume it would give you that, otherwise it'd be a big flaw, so then, but then I don't understand why it gives you that. Like, what is it that allows that? Because it looks like to me, it starts off, if it's above the line, it has to go up, so then is it changed by?
Yes, it is.
Okay, so
The position of the particle in the circular area is going to be changed by its
each
path.
subsequent measurement.
That's
actually
correct. That's correct.
Modifies it, okay.
That's
fine.
correct.
Okay. That was.
What you're guaranteed is if it starts off above the line,
Then it has
it's
to
going to
go.
end up somewhere in the upper sphere.
Okay.
Okay, but its exact position in the upper sphere is going to be a sensitive function of its position in the upper hemisphere before it went in.
I mean, it's a nonlinear dynamical system, so it's going to be chaotic behavior.
Maybe, yeah, but even if you have a highly symmetric situation like this, it's going to get moved around. Even if you preserve all these symmetries, the sequence of 3 experiments that you were just talking about is going to come out exactly in the predicted way.
And there's some dynamical equation that governs how it.
That is correct. There's what's called the guidance condition. It's extremely simple. Here's what it is. The velocity of the particle at any moment is equal to the probability current, the usually calculated probability current in the wave function at that moment divided by the density.
Okay. And it takes on a classical position and.
Takes on a determinate position. You know, classical is a loaded word.
Sorry.
It doesn't move around according to F=ma, but it takes on a perfectly determinate.
You've heard the WKB approximation.
Right.
Right?
Yeah.
Imagine running the WKB approximation. You get like a Hamilton-Jacobi equation with this weird quantum potential, and you also get a local probability conservation equation.
Okay.
Right? So the radial part of the wave function gets its own equation. It looks just like d rho dt equals negative divergence j,
Okay.
where j is rho, the density, times something playing the role of velocity.
Okay.
And the thing playing the role of velocity is the left-hand side of the guided equation.
I see. Okay.
So literally, you can almost see it popping directly out of the WKB approximation.
Oh, right,
If
okay.
you literally just do WKB and ask what's
Right,
playing
if you
through it,
want
Okay.
you'll see it's
or
guiding
even
equation.
without, you want to get something like a velocity
Right.
out of the Schrodinger equation. Just, sort of dimensionally divide the current by the density. It gives you a velocity.
Right.
That's the rule.
It basically turns the WKB approximation into an actual literal description.
So
of
it
the
becomes,
system.
WKB actually becomes the ontology rather than the.
And this is historically very interesting because, of course, Schrodinger discovered his equation by starting with the Hamilton-Jacobi approach and regarding the Hamilton-Jacobi equation as the aconal approximation. He ran it backwards.
Right.
So this is beautiful.
Okay.
Yeah.
Thank you. Sorry.
Anyway,
Everyone else understood this.
I still want to go back to my quote, philosophy unquote, about this whole business. You see, all the debates in the 30s between Bohr, Einstein, and all the others, and Schrödinger and so on, were always about non-relativistic quantum mechanics. Bell's argument shows non-locality, in my view, EPR Bell, within, well, of course, obviously non-relativistic quantum mechanics, but it's even independent of quantum mechanics because this is just a reasoning based on certain observations. So, and when you have the courses, you have the collapse rule and so on, and you have all these things which are mysterious, the students don't understand, and then you have all these problems once you start. If physicists knew the no-hidden variable theorem, then they will realize there's a problem because they have some naive statistical interpretation in the back of their mind. And so it seems that it's a huge progress to be able to get rid of all these problems which you do in the Broglie-Bohm. But each time I speak about that, I have people who jump at me and say, but what do you do with the quantum field theory, etc., etc. I want to say, well, wait a minute, okay? Because that doesn't apply to you, but still it applies to many people because people don't understand the Broglie-Bohm, and then of course they want to get rid of it. They just don't want to be left in peace. You see, I was discussing with somebody who was trying to talk to somebody else who is now dead, unfortunately, but he changed his mind before dying, but before that he was saying, oh, leave me in peace, I sleep well at night, I don't care, I don't want to worry about these things. You see, people say, no, okay, that's their attitude, what can I say? But it seems to me that there are many reasons to worry, given all the prime with simple, the spin, the detectors, everything within non-relativistic quantum mechanics, which as Bell says is 90% of physics, or even more than 90% of physics, and it does include all the things that, I don't know his name, that person was speaking about.
Matt Cleven.
Sorry?
Matt Cleven.
Okay, no, no. It doesn't change much to overlap, but anyway, I should know who is. But anyway, so these people, these things are not going to be, I mean, it seems to me that all these things, all these, they say, well, there's a quantum revolution, all these things can be understood. What is complicated indeed, it's not so much that there is no Bohmian quantum field theory, is that there are too many of them and it's not clear which one is correct. That's a problem because you can have particle theories, you can have field theories and so on, and it's not clear what to do. But I don't think the problem is simply except that none of these theories are really mathematically well defined, but that's also true for ordinary quantum field theory. So it's a complicated business. So I think I really think there's an enormous amount of prejudice against even asking the question. And the time lag, you see, now everybody's quotes EPR. They don't quote it necessarily for the good reason. They say, oh, that's the beginning of the second quantum revolution, the quantum information, so on and so forth. That's true. But that's not what EPR was saying. Why don't you look at what they are saying and why don't you think about what it means and what Bell did, etc. I mean, it seemed to me that, I mean, I've run into so many since, well, Tim is right to say that I've been discussing these things for years and years and years, decades now, with all kinds of people, including physicists, of course. And I see a lot of misunderstanding and prejudice and so on. So I don't think one can eliminate the prejudice factor.
So when its opponents throw Bohm into the flames, it just won't burn.
That's right.
But I have some foundational questions which aren't in any way opponents, but I didn't quite understand what your stance on were. One is exactly how are you thinking of the ontological status of the wave function? You might have said this during the talk, but I didn't get it.
Well, I don't know. I mean, I tend to be, first of all, I'm not a philosopher and I'm somewhat reluctant to.
That's no excuse.
It is a very good excuse. Obviously, you don't know how bad philosophers are. Anyway, no. Okay, the point is that I'm reluctant to, although I'm critical of positivism, in some sense, I'm reluctant to metaphysics also. So always of two minds, and I tend to agree with Shelley and others that it's nomological, the wave function. It's like the Hamiltonian, it's sort of part of the laws. But of course, we don't agree on what the laws are. So I mean, that's going to go the discussion.
Yeah, I thought that's probably what your view would be. And of course, this big issue, which we don't want to get into about exactly what laws are. But yeah, my other,
Do you have views on that?
my other question was.
Yes, I've used on laws. I know they're not yours.
My other question concerns exactly how you think about quantum equilibrium and probability. I know you like to talk about typicality, but exactly what makes a particular, particular typicality measure the right measure?
Actually, that you may be surprised, but I don't agree with my friends about that. I think the fact that psi square is the natural measure, I don't quite agree with that. I think there are situations where the uniform, for example, if you take particle in a box, it seems to be more natural to have a uniform measure on the basis of indifference principle. But that gets us into a
Well,
very
what would, in any case, what would make it the right measure if it's not, whatever, I don't know that natural helps much.
But you see, the problem is that you define probabilities that through the law of large number will lead to expectation, to empirical distribution, and then this empirical distribution sort of make your probabilities explanatory, or if your probabilities predict the right empirical distribution, then you can discuss whether your probabilities.
When you say define
I mean, nothing makes the probability true. That's what I would say.
nothing makes it the right probability.
Sorry?
Nothing makes it the right probability.
A posteriori, you can say that if the probabilities predict the right statistics, then you could say, then you can ask, but if your probabilities are very, very special, then take just coin tossing, okay? If you say assume 1/2, that's the indifference principle, that's fine. And if the statistics is 1/2 with many throws, many tossings, then you're happy. But if it's 3/4, 1/4, then you're going to try to find an explanation. And it's all.
I think I like that, is that the actual facts, actual results of measurements, or the actual positions of particles under various situations is what makes for the right probability. You connect it to the law of large numbers. I don't necessity to that. But of course, the law of large numbers is a theorem that results from repeated
Yes.
trials. But I don't think you need to have to say what probabilities are. I don't know whether you would think about it. Maybe this is a whole separate discussion. But your main idea is that unlike what you called your friends, this was at Shelley and Tim.
No, I have more friends than that.
I don't mean only friends, still a lot of friends. They think.
I thought of that, like, of course, he's dead, unfortunately. And then there's, of course, Nino Zanghi, and there's him, but there's also to move.
Anyway, but the difference you were saying is that they think the right typicality measure comes from some way what's natural. I forget what the term that
Equivariant.
Yeah, but I was going to use a term that's used. I think it plays natural with because it's invariant.
Yeah, but I don't. I'm willing to regard it as a separate postulate.
Right.
But I don't really consider it as natural as they do.
What makes it right, unless you rejected it, there's something about making it right.
Okay, bye-bye. Thanks for coming.
Is the actual results, okay? Anyway, great. I just also want to say it was a fantastic talk. It's really so great to have in one place all the things that's wrong with all these, especially with everything, especially the things that have popped up in 5 years. Sure, Paul.
He was, by the way, an old friend of mine. I've known since my thesis with a mathematician at the Courant Institute. Sorry? The guy who just left, Chuck Newman.
Yes, you go next.
Yeah, I'm sorry, I apologize. It was a very non-technical, very naive question, perhaps just terminological. I apologize in advance to Tim, who's been my recent tutor on these matters, if I embarrass him. Anyway, it's about the many worlds. You said that, in some way, when you've got these two worlds, say that both exist. You've got this world in which there's a live cat and this world in which there's a dead cat. Both of these worlds exist equally to one another. And it's just peculiar in a way you would think they both exist. So, or is it a more natural notion of world? This is why it becomes terminological. Isn't a more natural notion of world something that contains them both? Why, it's weird to say that you've got these two worlds, and it's got a world which has this and this in it, and call that something else. What they've got, they're not both worlds. They're parts of the world.
Yeah, of course.
And it's a bit like saying, somebody decided to call the northern hemisphere and the southern hemisphere worlds. I mean,
No, but the difference is that you can go from the northern to southern hemisphere, and these worlds you can't go from one to the other. They don't overlap. The wave functions don't interact. You see, for example, you could take certain experiments in quantum mechanics where particle goes through different paths, and you could think that when the paths are separate, there are different worlds. But that's not the case because they could recombine. It becomes only different worlds when you are dealing with a large number of particles.
Well, couldn't I have, this is supposed to be a kind of stupid example, but, a many trees interpretation of gardening, which means, when people naively said, well, you've got one tree, actually there are many trees there because there's all the different branches of the branches of the branches. We'd say, well, there's one tree and it has many little sub-trees in it or something like that. So why wouldn't that the right thing to say about the many worlds too?
Yeah, you want to say something? You can think of it like you can think of it like that, but the point of the separateness of the world is simply that once the wave function don't overlap and won't overlap in the future, then they don't interact and you can't go from one, like the hemispheres, you can go from one to the other. You just can't go from, compare what life is in one and the other. And the point, of course, is that they implicitly think that each of these wave functions represent a world, a real three-dimensional world, which I think is debatable. But that's what they think.
So this is just, so there was this big list of things to commit to the flames. Like Barry said, there's going to be a really big fire. There's one more thing that I presume you also want to commit to the flames, and which would have fit well on this list, but that you didn't have anything to say about, and which maybe this is just a suggestion for future versions of this talk. It might be good.
But of course, it will also be longer than 1 hour.
It can get unwieldy, right? But look, you mentioned two versions of GRW, GRWM, GRWF.
And you want GRW0.
I want GRW0, and it would be fun to hear, to hear the reasons for committing it to the flames. Not that you have to do it right now. I'm just pointing. I mean, if you want to do it right now, that would be great.
Well, the point is that I don't feel like being a vector in a Hilbert space. That's my problem. I mean, you see.
That doesn't sound very.
Well, you see the problem. No, wait a second. Wait a second. I think I will agree with Tim on that. You can correct me, but I am a naive guy who believes that 2 + 2 is 4 and 4 + 4 is 8. As Don Juan said to his Don Juan of Molière's Don Juan. I mean, I believe, of course, I live in a three-dimensional world. There is time, and then there is matter, and all these things populate the three-dimensional world. That's my starting point, okay? And I believe that experiments have results, and of course, the whole of science, of course, assumes these things. The whole of science assumes a lot of commonsensical notion. Now comes a guy who says, aha, but you don't realize that the Earth is older than you think, and there are all these species, and the Earth doesn't rotates around the sun, not the other way around, even looks the other way around, and there are these atoms and so on and so forth. That's true. So common sense leads to science. I mean, Russell said that common sense leads to science, and science refutes common sense, so common sense is false. But common sense is false only when science really gives you argument without common sense.
Right.
My problem with this, I know your view on that, I heard you before. So, I mean, my view of this idea of the wave function, define that the world is really a wave function in a high-dimensional space, and there is nothing in 3 dimensions, sort of an illusion. I mean, you sort of reconstruct 3 dimensions out of that. Seems to be, why? I mean, why would you do that? I mean, it's not true. Wait, it's not true that the success of quantum mechanics commits you to that. It's not true.
Right.
No, that's all. So,
and indeed, as you rightly said, you would be committed to the failure of quantum mechanics if you believe any version of the GRW theory.
That's true too.
So it's not. So the reasoning certainly isn't the perfect success of quantum mechanics.
No, but I don't know what the reasoning is, and in any case, you could of course do that with Bohm. You could say, well, I mean, that's your marvelous point. You could take a point in high-dimensional space, have a wave function defined on this space, but I was discussing with Shelley that, and so I thought of various questions. I mean, one is, since you like, Jacob likes particle creation. If you have particle creation, then your marvelous point changes the space. And then, of course, if you introduce fields, okay, then the fields, since people love quantum field theory so much, you must realize that quantum fields are not even functions, they are at best distribution. So now you have your marvelous points, points a space of distributions, and it just looks to me so artificial and so complicated. Well, anyway, so your favorite opponent is...
One can weigh, one can weigh advantages and disadvantages, and your sort of thought that there's a general principle of conservatism operating in scientific progress to the effect that you should only give up those parts of what you started with when there are compelling reasons to give it up. Yeah. I agree with that 100%. I don't, people who hold these views like me don't hold them because they think they're cute or because they think they're wacky. They must think, you must know that they must think that they have some explanatory advantages, that they have various other kinds of advantages. So if the thought was, we don't want this because the only thing it has to say for itself is that it's counterintuitive, you can't believe that. Okay. Maybe these people are deluded, maybe they're weighing things incorrectly, but obviously their motivations are or at least what they take their motivations to be, are exactly in the form that you outlined. These kinds of theories have some advantage, which constitutes a compelling reason for this kind of a departure from the manifest image. From what.
Yeah, but to me, it's such a radical departure, and I could go to very many more objections to that. Number one, it's a very. I will give James in a minute, but a very radical departure. And if you take atoms, for example, when not everybody accepted atoms, and people who didn't accept it were perfectly rational not to accept them in the first place. But when you counted, when you have Avogadro's number, and you had so many ways to count Avogadro's number that were different and give more or less the same number, that's what I call compelling evidence. But there is no compelling evidence for the wave function being defined. You see, that's okay. The world being a wave function. And as I say, what do you do with the spin degrees of freedom? You are a vector in a Hilbert space. That's what you are in the end.
No, you have a wave function in something isomorphic to configuration space. But it's obviously a long story. All I was saying was, it would be you had succinct and for the most part, I would say compelling reasons for committing all sorts of things to the fire. That
Not
might
you.
be- that
No, I
might
knew
be-
you were going to be there, so I didn't put you on the list. Consider it.
This is a fight that was just 2 weeks ago. We engaged in here too, but Tim, you go back, Dan, you take over.
Yeah, so, I mean, can I just, and I think this is a bit in the spirit of what David said, but it's also in the spirit of just effective rhetoric, right? I mean, I said you were spicy, and I chose that accurately. There's a certain point where if the rhetoric gets a little too extreme, it then dilutes itself. Okay? You started out by saying, well, there's this idea, and I have some responsibility maybe for this idea that there's this trilemma, you know, because I did write a paper with it in it. I'm not sure it was written that way before that. Maybe it was.
Yeah, of course.
But saying, look, either, you know, you've got, is the wave function complete? Does it always evolve linearly?
Yeah, but I agree with the logic.
Yeah, so, and there you say, look, you know, those are just three incompatible claims. You've got to give up at least one. So if you're going to give me a theory, it would be really helpful to start out by just checking the list, right? I'm going to keep this one or give up that one. You know, something like Cubism, I mean, that's not even, I mean, that's really way off the map from these other things that are, I've been trying to come up with what I would call a theory. And then the problem I have is that I understand you have objections to certain approaches, but an objection to a theory that's a pretty well-defined theory is a different thing than a criticism that what we have before us just isn't even in the game of trying to be.
I agree. I don't
If you
know.
run them all together, you sort of miss where just judgments of I find this very plausible, or as David says, I'd be willing to give up this to gain that. I mean, these sorts of things, they're just a different, you're playing a different game once you have something concrete on the table before you.
Of course, I don't
So I
mean.
think lumping them all together.
No, I didn't mean, okay, by using, I mean, this was sort of a joke to commit it to the flame, but because it comes from, you know, very well whom. So and since you like being human, I mean, no, that's sort of a joke. I didn't mean that all these theories were to be put on the same footing, but we discussed that before, huh, Tim? I mean, about your book and so on. It seemed, I mean, I was even discussing that with Shelley. I guess I spent a week with Shelley, so lots of discussion. You see, you don't discuss Copenhagen in your book, but you discuss many worlds. I mean, that's a choice. And it seems to me that many worlds is really inconsistent. I maintain it's inconsistent with the Born rule, and so it's not empirically adequate even. Of course, Copenhagen is.
I can't see that as even a proposal for a theory as I understand the theory.
That's true.
Right. And many worlds I can at least understand what they're trying to do. I can understand some of the commitments they've made and, you know, trying to work within those commitments. So it just seems to me a different kind of project. Whether it ultimately can be worked out, maybe it can, maybe it can't, but at least I know what it would be to work it out. I don't even know what it would be to work out Copenhagen, right, in a rigorous way, because it just doesn't seem to me to have the, you know, the resources to do anything particularly precise.
Yeah, okay, but the problem, you see, the problem with Copenhagen, and that's why Cubism is a bit of a hair of Copenhagen, is that it's really a philosophical attitude. It's basically, you can also sort of do it in the instrumentalist way, okay? When I say I don't agree that three realist theories, I don't mean that the two others are not realist, but they're not realistic. I mean, they're not realistic proposals. They're realist proposals in the technical sense of realism that you and I agree with, but I don't think I still think that, you know, to be weird, too weird to be accepted. And I think once you understand the Broglie-Bohm, you realize, I mean, you see, there is nothing approaching in the other theories, approaching the beauty of how in the Broglie-Bohm you see what measurements mean. and why measurements don't measure. I gave two examples. You can measure something that doesn't exist, and you can measure something that does exist and get the wrong result. And nevertheless, the Broglie-Bohm explained to you exactly what happens. It seems to me that is something which I don't see anything like that in many worlds. Many worlds and GRW are still focused on trying to solve the measurement problem. Certainly GRW were thinking of
Well,
solving
they
it.
think that they've solved the measurement problem.
Yeah, they think,
They do, right, they don't.
but that's not the measure. Well,
But I think the reason,
no, maybe they do, but I don't care about the measurement problem. I care about the ontology problem.
yeah, so they have no answer to it. So, yeah, that's right, but what they do think, and this came up, I think, earlier in Matthew's point, is that you can apply many worlds to extend it to quantum field theory. But of course, it has no solution to what really is the basic problem. And you run into the trouble of the extensions when you come up with some sort of solution to the ontology problem.
So how does many worlds not solve the measurement problem?
How
Why has it failed to solve the measurement problem?
many worlds?
Yeah.
Because it doesn't, it solves, just to solve the ontology problem. What you here have is a wave function. Where are the cats? How do you get cats out of the?
Emergence is playing a very, is being heavily,
It's
somehow emergence is
Somehow.
Well,
responsible.
it postpones it to the point of why there's.
The details are gonna be filled in, but also the problem is that in the measurement problem, you wanna get probabilities out.
Right, well,
So
yeah,
we
yeah.
count
I
the
mean,
measurement
I put
That's
aside
the other
Warren.
part. That's the other
Warren.
And that's
That's
proved
much
very
easier.
difficult. I mean, David Wells wrote, you know, enormous, beautiful textbook in 2012 called The Emergent Multiverse. And most of the book, or not most, a very large portion of the book is devoted to trying to explain how probabilities come out. And he proves theorems, it's a beautifully written book, and he doesn't manage to do it. And if someone as smart as him, who writes a book that extensive in 2012 can't do it, I don't know how many more pages do we have to write before we can do
By
that?
the way,
Which book are you talking?
chronologically,
The Emergent
That's-
Multiverse.
That's what they mean, but
The board
that
will-
solving the measurement, you know, part of what you want from solving the measurement problem is not just that measurements have determined outcomes, but that they have them with the right frequency.
Right, because in Everett, you get what look like determinate outcomes, but the question is, how do we get probabilities associated with it? And that's-
Okay,
You're not going to
okay, fine.
I can't go to dinner. I got tickets or something.
Ah.
I just go, but thanks. That was really a super talk. Have a great dinner. Maybe we'll be in touch by email.
Okay.
Let's see. I have.
If you want to meet tomorrow, let me know.
So, 1, 2, there's.
Yeah, I mean, I don't, because
Diego, you're coming to get rid of that?
Yes.
Six.
I'm not coming.
You're not coming.
well, we reserved 8
8.
places.
Yeah, we know you're no one there.
At least the beginning.
So
I may have to leave.
I think anybody wants it.
Yeah.
Orna, I mean, I think Orna's gonna, did Orna call you?
Yeah. She said she'll meet us at the restaurant.
Okay. At 6?
Yeah.
Where's the rest, what restaurant?
We did Bushuri,
It's over on the
you
other
know, we
side.
did Bushuri Gay and.
It's on our place.
We'll stop by our place anyway.
Okay, thank you.
So the recording should be on your.
No, I'm very.
I
As I
will
was
send
mentioning
you
before,
the.
we have this